usual for a professor. It's a pleasure to introduce our next keynote speaker. And originally we had outlined a full-day program, and I apologize, I guess maybe to the keynote speakers and also to the audience, that the keynote speeches and everything had to be compressed to fit into the time that we were allotted. But we're really grateful to have a half day to focus on this. But it's a pleasure to introduce Bruno Gaeta. He is in the Department of Computer Science and Engineering at the University of New South Wales. And he has the distinction of being director of the bioinformatics. It's so unusual to hear this title for a program, bioinformatics engineering program, the largest one in his continent, at least the last time I asked him about it. That's still true. And really, one of few such programs in the world. I believe that you guys were kind of ahead of the curve to recognize that this is an area that's important to train in. I think other bioinformatics engineering programs will emerge. So he's going to talk about bioinformatics engineers. Bruno's also a glutton for punishment. He served on the ISCB board of directors for roughly a decade, and that wasn't enough punishment, so he ran to become the ISCB treasurer, which he is now serving in that position. And Bruno's also the co-chair of the committee that oversees the regional affiliates of ISCB. So Bruno, you want to?
Thank you. I used to be co-chair of the education committee as well. So as Lenny mentioned, I've been involved in bioinformatics engineering for a while. That came through partly because when I joined UNSW, I joined the School of Engineering. They had a program in bioinformatics. They wanted to put one together, but they wanted to one that allowed them to escape the strictures of the Bachelor of Science. So in order to be able to have more freedom and to create their own program, they called it bioinformatics engineering. That was in 2001. And really, it turns out that this is a good idea. Probably to take all of the blame for this idea of having engineers' competencies in the ISCB competencies. But this came out really out of this diagram that I've been showing to my students every year, the students that start. Of course, we haven't seen bioinformatics before. When I try to explain, rather than try to discuss what is bioinformatics, I try to show what do bioinformaticians do. And that starts with a biology problem. And there is a process through which you abstract the problem into computational mathematical terms, and that's computational biology. These are the people who we see a lot of at this conference who are into taking biological problems and coming up with novel solutions to deal with it. But then there is a process of taking these algorithms and turning them into software that actually works, and then into infrastructure that works, in order for it to then be used by biologists who are going to do discovery in biology. Now, in many cases, bioinformaticians do all four of those. But in larger cases, in many cases, it's split. You will see people that are really interested in developing algorithms and working at the theoretical end, and not really dealing with the application. You see a lot of biologists who use computers these days. We've heard from most of them. But they do not know what goes on before. And for a lot of software, there are those intermediate steps where you need to go from an idea, maybe a prototype, to build an infrastructure. And this idea of being able to design an infrastructure is really engineering. So this sort of thought pervaded our discussions of early competencies. And this is from the second of the papers that came out of this task force. highlighting the fact that especially with the increase in size of data, and there needs to be people who have not only the computational biology, the theoretical end of things, but also the practical skills to build something that works, to build something that's robust, that can handle large amounts of data, something that you're going to be able to put into the hands of biologists, of clinicians, people who may not have much computational training, so that they're going to be able to use it and to use it in a safe way. And as bioinformatics is moving more and more into the clinic, and it's going to be used for diagnostic and so on, it becomes more and more important. You really want those bioinformatics tools to be solid, to be validated, to run well. So we're talking here about people who, in addition to strong scientific foundations and technical skills, they need to bring to bear engineering competencies such as systems design and project management. So this is really the kind of thinking that that underpins the bioinformatics engineering program. Even though our students, we try to train them to go across the board, they need to also be computational biologists, and they need to be able to use the programs to some extent to do discovery. But we try to emphasize this engineering aspect. So you've heard about persona as a way to conceptualize really your students as part of course design. And this particular persona is one that we're using, and it's actually based on some of what my students are doing, some of what my graduates are doing when they're working in large medical research institutes that are branching into dealing with clinical data and patients. So they really need to have a really solid bioinformatics infrastructure. They build pipelines for processing large amounts of data, and on top of that, to assist the scientists in the institute. So showing the sort of things that he's doing, but most of it is computational work. So it's one of the persona that I use when I think about the program when it comes to revising it. And this is the program itself. So the Bachelor of Engineering in Bioinformatics Engineering started in 2001. It is the oldest surviving undergraduate bioinformatics degree in Australia. There was a large number of programs that started in the 2000s, and most of them died because of not so much students. And now it's picking up again. It's becoming fashionable again. As I mentioned, we designed it originally as an engineering degree because we wanted to have freedom in choosing what we could have as part of this program. When we wanted to be out of the constraints of the Bachelor of Science, which was a bit more regulated. But it turned out that as an engineering program, you need to be accredited as an engineering degree. And this program is accredited as an engineering degree, meaning that the graduates are recognized as engineers, and there's international codes, the Washington codes, that mean that they can work as engineers all over the world. But that means that every 5 years, we are visited by a group of engineers, and some of them are quite old school mechanical civil engineers, and they look at the program in extreme detail. They want everything printed out to read their things. They can't read it, but because this is the amount of documentation from the floor to here that we have to give them a program in order for them to decide whether we qualify as engineering program. It is a 4-year program, and every time we go through accreditation, it involves more revision, often at the expense of the biological content, because the engineers want to see more engineering. But as part of that, what they force us to do, and what they force us to do since the program started, is to think in terms of competencies. So the way in which the programs get evaluated and get accredited is based on competencies. So Engineers Australia have a list of core competencies, or what they consider a graduate engineer should be, and they want to see how the program meets all those targets. Now, on top of that, the university administration, thinking it's a great idea, has implemented that across all the programs across the university, even the non-engineering ones. But in that case, the competencies are what they call the graduate attributes. The competencies they expect all the graduates of the university to have. So every 5 years we have to go through quite an intensive process of accreditation for like Engineers Australia and ACS, which is the Australian Computer Society. And the key process here is curriculum mapping. That's where you take your program and compare it to those core competencies to see whether everything aligns. So since I was already doing mapping two sets of core competencies, Engineering Australia and the university, it's not a big stretch to actually do it also with the ISCB competencies, and they highlight slightly different things. But the process is the same, and I'm going to show you the process as it's being put in place by the university for the Engineers Australia and for the graduate attributes. And you see it's actually quite a codified process. Whenever we create a course or a module, a class, we have to list our learning outcomes. So this is here for one of my courses. The name just has been revised to apply bioinformatics, because apparently getting methods in the name of the course scares off biologists. So you have to map your learning, you have to list your learning outcomes, and I'm sure all of you who do course design need to do that. And then you click on the next tab, and you've also got to list your assessment tasks. Now all of that has got to be aligned. And the way in which to do that is in the next tab, once you've done both your assessments and your learning outcomes, you map one to the other. So this assessment task assesses these learning outcomes, and so on. So the system actually builds a matrix for you, based on how you define it. And then you also map the learning outcomes to the competencies. So in this case, it's the university graduate competencies. And you do that on a course-by-course basis. So this is for one course. But then that system, who I can't claim credit for, of course, put together by one of my colleagues, allows you to do the mapping over the entire program. Puts together all the courses from the program, and at the end of it, you look at the bottom, and you should see pretty much all your competencies, which are here, should be colored. You've got this heat map of competencies. So that allows for, it's a very nice tool that allows you to actually check that your program meets those competencies. So the engineers, accrediting bodies love this sort of thing, because all we need to do is look at this matrix and tick, it's gone, move on. So I don't have the tool for the ISCB competencies, but the process is the same, pretty much. You want to map your learning outcomes to competencies, and you want to map your assessment to learning outcomes. Ultimately, your assessment is how you can tell whether our competency is being reached or not. So, by having learning outcomes, assessment, and competencies that align using this sort of approach, it's an easy way to tick the boxes. But it's also a way to identify the gaps, as also as mentioned. It's a way in which you can then go and revise the program and fill in the gaps in competencies. Now, this is the Bachelor of Engineering program. Just for comparison, I want to also show you a more recent program that I've put together, And I got that because there were some students who wanted to do bioinformatics, but they didn't want to do all the engineering part of it. They were more interested in being bioinformatics scientists, people that are using bioinformatics and not as thoroughly technical. And that's part of the Bachelor of Science. But what it does there is provide a nice comparison with the Bachelor of Engineering, so we can see the differences between those. So here we've got the Bachelor of Engineering, the Bachelor of Science. What I'm highlighting in red are the differences between them. So this is in first year, the engineers do software engineering and computer systems and physics, whereas the scientists do more chemistry and a bit more science. In second year, the engineers do engineering design, object-oriented design, discrete math. The scientists do more science. Now the ones that are underlined here are the dedicated bioinformatics courses as well. Now the scientists still do a little bit of programming, but they don't get to that level of detail of technical proficiency. In year 3, the engineers do algorithms and databases. The scientists, well, they get more relatives. And in 4th year, the engineers get an extra design course here. They do management and ethics. So there's a kind of a hybrid course that combines project management and ethics that all engineers have to take. And they both do thesis projects. But the science thesis project typically is larger than the engineering thesis project. So I'm showing you the kind of the rationale behind all that essentially came by looking at the competencies and identifying which areas should an engineer have that a scientist doesn't need. But, so the next few slides just highlight those dedicated bioinformatics courses, some of which are very technical, some are less technical. They're more about towards applying bioinformatics. A lot of the design behind these courses has come from also the necessity to have students take those classes, to have enough students take them so that they're viable. And for that, it means that we need to get science students, even biology students, being able to take those courses, even if they haven't done programming before. So we split our courses into courses that can be taken without programming and courses that require programming. So those two there can be taken without programming. This one we introduce a little bit of scripting, a little bit of R, but we don't require them to have any programming. This one is purely about using existing software, so we don't really concern ourselves with programming here. In contrast, those two courses are design workshops, and that's again a little bit of politics, but when you're dealing with Engineers Australia accreditation, they like to see design. So a big characteristic of an engineer is the ability to design solutions. So they're looking at problem solving and design. So we're almost forced to include the word design in our course titles, so that the accreditation bodies like what they see, and they see that there's enough design there. But these are actually project-based courses where the students have to build a bioinformatics application, a piece of bioinformatics software over the course of a term. And they do that in collaboration with an academic somewhere else in the university, either in biology or in medicine. Who kind of acts as a customer, and they really have to put in place the entire engineering design process there. So these are those 4 courses. The next slides here just give the 100 countries for those 4 courses. I'm not going to make you all read all this. But in conclusion, really, the main thing to take out of that is the fact that we really have a lot of different constraints to play with. We need to work both within the ISCB competencies, but also within the engineers Australia competencies, the ACS competencies. And that is a little bit restrictive, but also in the end actually ends up with I think a better degree, one that is really streamlined and achieves what it's meant to deliver. Thank you.
I think we have time for one question while Kathy's loading the slides.
So the way we work, those persona, and this is not the only personality we use, but this is what the first one, because the most engineer one that so I want to put it in the top. I get those from talking to graduates. The advantage of categories on this small degree, I get in touch with a lot of my graduates, I know where they're working. You can ask by all over Australia, so they know the world, so this is the world. And for many of them, I have continuing discussions about what sort of job they're doing. And so I'm very informed the design of the program as well. So I look at what those graduates are doing. So it fits from the graduates rather than from the entry-level students. Usually, because we get our students straight out of high school, many of them, surprisingly many of them don't even know what bioinformatics is, and yet they take a degree, they enroll in the course for secondary school. We try to design based on the jobs and the careers that are going to be at the end.
Yeah, like kind of on the recruitment side, right? Like, I mean, do prospective students actually see kind of the importance of these skills for people's career at that young age, right? At 18, or is it more like after you graduate, then after you graduate with a bachelor's, you realize you need these skills. So that curriculum might be more suited for a master's course instead of.
In Australia, we tend to specialize early, which means it's good to be there at an integrated table. The other advantage of being there at the integrated table is you get students straight out of high school before they forgotten either their math or forgotten their biology, which is the issue when you do a master's type course. You get 3 years where they specialize in biology, they forget the math, or vice versa. Our marketing department, usually all the marketing materials have got introduced of class students. Graduates that say, I did bioinformatics, I really love to be glad I did bioinformatics because this is my job now and I'm looking to do this and doing this.